I had a few questions after the lecture, and so between the two lectures now. One question concerned the question of, well, so what do we do with this posterior? Like, how do we interpret this posterior? So one person came to me and said, okay, so now I have this posterior, okay? How do I interpret it? What does that mean? Well, so the first thing this person said was, I can just go, so does that mean I have to now go and find where the maximum of the posterior is? Yeah, you can do that. There's nothing to stop you from doing that. But the posterior is so much more than just where it peaks. It has a lot of information in it. It tells you not just what the most likely parameter value is, which is where it peaks, but it also tells you about the relative probabilities of all the other possible parameter values. So, for example, if you really believe in your Bayesian analysis and in the prior that you chose, we'll talk about prior selection as well, then you take your paper where you've worked hard and you've derived your parameter posterior from your CMB data today, and then you are ready to place bets about the true parameter values. And so you could open up a market, okay, a betting market, where people place bets on the parameter values that will be obtained with, let's say, the CMB stage 4 mission. Let's say in 10 years roughly, we'll have much better parameters from CMB stage 4 compared to what we know now. So you work very hard, you do your parameter analysis, you get your Bayesian posterior today. This is with the data that we have now. And then you're asked to bet on the true value of the parameters. And the true value of the parameters, or at least, of course, in the future, it will also be a posterior. You will never get completely rid of all uncertainty. Okay, but to simplify the story, let's say you have an oracle that at some point in the future reveals to you the true baryon fraction in the universe, for example. Okay, so how do you place bets about that baryon fraction of the universe? Well, this probability distribution, it's a natural probability distribution, so you can interpret it as telling you the betting odds for different let's say theta is the baryon fraction, for different baryon fractions of the universe. So, for example, a bet of this baryon fraction versus a bet of this baryon fraction, let's say this is roughly half, you should be paying roughly half for this bet compared to that bet. Okay? The betting odds, so this really is it can be interpreted as the betting odds for the value the parameters that you have here. You can use it, so this is for the posterior. Now, with this new information of the posterior, we can now use this to predict stuff, right? We're scientists. We're in the business of predicting things. We have models to predict observations, for example. So what we can do with this is we can predict observations of tomorrow's experiment. Okay? And we have better predictions after seeing today's data, because our posterior now is narrower than we could have predicted yesterday, for example. So we can predict tomorrow's experiment, a future experiment. So what do we have to do to predict something? Well, we take P of d given theta. So if we knew the true parameters, we could predict the future data. Let me call this d future. So let's write prediction, okay? Let's call this a little section of our prediction. We can predict, so how to predict future data? D future. Given d today and a model M, let's say. Okay, how do we predict that? Well, so if we knew the true parameters, we already have the answer. It was already written down somewhere over there. No longer there anymore. Remember what I said? The likelihood is kind of a bad name because it doesn't tell you really what it is. The likelihood is the predictive density for the data given the parameters. So that's exactly, if we knew the true parameters, we would predict the future data by drawing from the likelihood. Okay, the likelihood tells us the probability distribution of that future data. So given theta, it's P of d future given theta. Okay, so this is the likelihood for the future data, meaning, your future data set might have some, whatever the noise sources are of the future data set, that will have an impact on what this probability distribution is. But this is so the likelihood is the thing that predicts your future data set. Now, but we don't have the true parameters. So given theta, this is true. But let's say we only have partial information about theta. We only have the current. So what if we only have, if we only have, d, so P of theta given d now, okay? The data now. Well, so if we knew exactly what the probabilities, what this is, if we knew exactly, that would be that. So what we can do is we can chain the two probability distributions, right? So given that we have the data now, we can say, what is a possible parameter value? And for that parameter value, given that parameter value, we can predict the future, okay? So one way to write this is to say, so let's write the joint PDF of the future data, the true parameter value, and the data we have now. Okay, so we have now a joint PDF of three things. We've learned that we can split joint PDFs into these factors, conditional times marginal. So let's do that. So I can do P of d future. So this is equal to P of d future given theta comma d now. I'm going to group these together. I can always just make a longer vector where I put both of them inside, okay? So I can group these together, given those two, times the marginal, P of theta comma d now. I think you may already see where this is going, because I now have a joint PDF over those two. I can split it again, okay? So let me split this again. So this is P of theta given d now. Is that what I wanted? Right, times P of d now. But actually, what I should have done is conditioned on data now right away, because we already have the data now, okay? So, sorry, let me correct that. I apologize. We're going to make a conditioning bar here. Well, this is already to the right of the conditioning bar, so the only thing I'm pulling over the conditioning bar is theta. So then I only have, because I'm conditioning here, when I put this over, I still have to condition on the data now there. Okay, so then the only thing that goes away is this probability distribution, which is useless because I have the data now. So it's all conditioned on the data now. Okay. Happy? Hope you didn't feel like I was pulling a fast one on you. Just wrote down the too general thing here. Okay, but we can condition on the data now because we have it. Great. So I don't need to write this. So this almost looks like the likelihood. This is the current posterior, so we have this. We know how to simulate, we can draw theta from this. What about this now? The likelihood was this, but it's also conditioned on the data now. And here is a concept that is extremely useful, which is the concept, remember we talked about independence before? Well, now we're going to have a concept of conditional independence. Okay, so let me have a little insert here. Okay, conditional independence. So conditional independence. Conditional independence is a situation where, so if P of x given y and z is equal to P of x given y only, then we say that x is conditionally independent. X is conditionally independent on z, of z, given y. Okay, so this seems a little abstract, but let me illustrate this. So if P of x given both y and z is the same as P of x just given y, then what this means is that any knowledge, if we know y, any knowledge that we might have on z doesn't add anything, and doesn't add anything to our knowledge about x. That's what that means. It's another way of saying it, more colloquially. So if I know y, it already tells me everything I could possibly know about x. So given y, x becomes independent of z. Okay? So for example, in this case, I'm using the data to constrain my parameter here, right? But if I already know the if I have perfect knowledge of the parameters, this data doesn't add anything anymore. I already know the parameters perfectly. If I assume a fixed value, true value of the parameter, well, I can take as much data as I want. It's not going to change anything to my knowledge because I already know perfectly this parameter value. Okay? So in that sense, whatever I predict about the future data does not matter on what data I have now if I already know perfectly the parameter. Right? So another way of saying is the future data is conditionally independent on the current data given the true value of the parameter. Okay, it's a little bit slightly, I hope it's clear enough, but I realize that it's a slightly subtle concept. It's not really that complicated, but you have to say it to yourself a few times before you, if you understand it. So, so if the future data is conditionally independent, which it often is, most of the time it is, on the current data given the parameters, then this just becomes P of d future. So this is assuming conditional independence of d future on d now given theta, then P of d future, this becomes P of d future given theta times P of theta given d now. Okay, so this joint PDF here of the future data is actually the product of your current posterior times the future likelihood. If you wanted to simulate future data, what would you do? You just draw theta from a current posterior, and then given that value, you draw your future data set from a simulation of your future data. So this is how you can predict future anything with imperfect knowledge of the parameters. You can sort of see what is happening if you knew the value perfectly. If this was a delta function, right, then this would just be your likelihood. But now that you don't know this perfectly, this is a distribution. So this distribution here, this predictive distribution, will get smeared over all possible values of theta, right? This will take all kinds of different values of theta. It would sort of you would sort of average over all of those different parameters, over all of those different likelihoods for different values of theta that are allowed by the current data. So in that sense, you can use the posterior to predict the future by folding in all of your current uncertainty. So it's how to predict under uncertainty. Questions? So this is one way you can use the posterior and how you can interpret it. So the posterior really is the end product of Bayesian inference. Yes? What? Here? The first term, this first term just depends on your model of the future data. So if you have an instrument simulator for your future satellite, you stick in a parameter value and you draw out some data. Yeah. So likelihoods basically give you the probability distribution that you can simulate, that you simulate from that you draw from by doing a simulation. That's what a likelihood is. So I was saying the posterior is the end product of Bayesian inference, okay? If you, for some reason, if you don't want to quote the posterior, but you want to quote just one number, let's say you have a boss, your boss doesn't care about statistics, just says, I don't want you to produce probability distributions, I don't know what to do with those. I want a number, give me that number, and if it's wrong, you're gonna get punished. And I suppose there must be some bosses like that. How do you act then? Actually, that's an interesting question. I don't want to take the time now to go into this, but in fact, that then becomes a decision problem. Like, how do you summarize this PDF in one number in a way that minimizes your future loss of the punishment that your boss will give you once the true value comes out? You can phrase this more positively in terms of a reward, but okay. And it turns out that if your punishment is the square of the error that you make, let's say you have some oracle, some way you're going to find out the true value next month, and your boss then evaluates your prediction, like how you summarize the posterior here into one number by saying you take the square difference and subtract that from your paycheck. It turns out then the optimal thing to quote is the mean of this posterior. So it's the posterior mean, not actually where it peaks, but where it has the mean, because that minimizes the expected squared deviation. If you have a really, really unpleasant boss who says, okay, you're only going to get your salary next month if you give me exactly the right value. You're just a little bit wrong, 0 salary. That very unpleasant boss, I mean, you almost certainly, unless it's a discrete situation where there's a finite probability of actually getting something. So in that case, what you would quote is actually the maximum, because that gives you the maximum probability of getting getting your reward next month. And if you have a kinder boss who says they will punish you by the absolute linear difference, just absolute difference of the true value and the thing that you quoted, then what you want to quote is the median. Okay, and those are easy results to obtain if you just write down, you minimize like the squared deviation, you minimize the mean, the absolute mean, you minimize just doing derivatives, or you minimize the total, you maximize the probability of getting it right. Those give you those different results. So these are, that's then a question of making decisions under uncertainty, right? You're deciding, how do I summarize this posterior? And the answer is given by assuming some loss function or some utility function that you then minimize. So that's just as an aside. But that's how you can use the posterior. You can base your decisions about your actions on this, because this is this gives you the relative probabilities of things happening. So you then can make decisions based on that. Okay, there was another question, which was, what if my theta isn't just one number, but what if it's a whole list of numbers? And that will typically be true for the data as well. Now, I've been drawing two-dimensional plots, d versus theta. That's because I don't know how to draw 152 dimensional plots. And really, you could just see this as like if I write theta, what I mean is that this subspace along this direction has n theta dimensions, and this subspace in this direction where the data is has n data dimensions. And while I cannot draw it, a lot of the intuition you get from this simple two-dimensional diagram transfers to the case where you have more than one parameter and you have more than one data number. See, there were some other questions. Oh yeah, so there were other questions which I will now get to. Actually, because I want to talk about what did I do first? Are you happy with this stuff, or do you want me? I can give you one more example of a very, very simple form of inference, like another sort of. I'm not going to write it out, but I'll talk you through it. Or I can move on and we can talk about comparing different models. So let's have a show of hands. Who would like me to give you another few minutes talk about, for example, that addresses part of the question that we had earlier about like where does the randomness come from and so forth, like what is my model and so forth, for a specific example, trivial example, or we can move on. So who wants to hear the example? Okay, I think that's already the majority. Who wants to move on to model comparison? Sorry, I think you lose. Okay. All right, so the simple example is let's say I want to measure the height of this table. Okay, so first of all, if I want to write down this joint PDF of theta, my parameter is the height of this table. My data is, I don't know, I want to measure the height of the table in units of how many sponges it is high, okay, for example. Some unit. Let's say I have a measurement device, okay, so I can measure it. All right, so how do I proceed? So first of all, if I want to generate this joint PDF, I need a prior, right? So what is my prior for the height of this table? Any ideas? Always, it's positive. Great. Okay, so we can already exclude 0 and below. Excellent. Okay. The ceiling is higher, so we know it fits in the room, so it has to be less than the height of the ceiling. And probably has to be larger than the size of a hydrogen atom. Don't know how to build tables that are smaller than that. Okay, so you can see we already know something before we even started. Okay, so that's the idea, to get this notion that we already know something. Or maybe, because I looked at it, I have data, right? I've looked at it, and I know already that it's less than 2 meters, and it's probably roughly 1 meter, but I'm not quite sure. It's probably 1 meter plus or minus half a meter. And so I could make that a Gaussian prior, where I say I have an informative prior because I looked at it, and it's maybe 1 meter plus or minus half a meter just by eyeballing it. Okay, so that would be one way to get your prior is to use prior information, which is by looking at it, estimating from visual inspection. And if I have a mean and a variance, it turns out actually if you just have a mean and a variance of something, or mean and standard deviation, the PDF you can make up with that mean and that variance that adds the least amount of extra information, but that has that mean and that variance, is a Gaussian. So if you want to be conservative, and you want to have a PDF that has a mean and a variance, then you can choose a Gaussian that encodes the notion of, it has some value, but it's uncertain by a certain amount. Okay, so this is useful to know. Maybe prior choice. The Gaussian PDF. Let me write it down. We need it later, so I thought I'd write it down now. So let me write it G of X, mu, and C, which is e to the minus a half x minus mu, C inverse x minus mu. I'm going to write it multivariate. Why not? You guys are smart. do it right away. And this is the determinant of 2 pi c. So c can be, let's say, for 1D, it's the variance. For more than 1D, it's a covariance matrix. Mu is the mean vector, okay, is where the Gaussian is located. C describes the uncertainty around that Gaussian, and X is just the value that you're giving describing with the PDF that you're modeling. Okay, so this Gaussian PDF is the maximum entropy, least informative. Let me write least informative. Least informative, or maximum entropy PDF with mean mu and covariance C. Okay, for 1D, it's just the variance. Yes? -1. So this is an analogy to the 1D thing, which is e to the -1/2 x minus mu squared divided by the variance squared. Okay, so this C is a kind of squared quantity that expresses the width of the PDF, except not just in 1 dimension, but if you have 2, 3, 4, 5 dimensions, it actually expresses the combined width in all of those dimensions. So this is a multivariate generalization of this one-dimensional thing. Okay, so, and the -1 expresses that it's in the denominator of the, okay, so back to the example, we have an informative prior, let's say a Gaussian informative prior, fine. Or we want to have a very uninformative prior with some bounds, let's say a bounded flat prior, like larger than 1 hydrogen atom, smaller than the height of this lecture hall. Even that is actually informative. The point being that even if I know your general instinct, like your general, you've been trained as scientists to always want to assume the least possible amount of information. And somebody actually asked me before, so what do I do if I have no information? How do I choose a prior if I don't know anything? Well, most of the time, if you really think about it, you do know something already. It's just maybe hard to quantify exactly what you know and to put a PDF on it. So then you could use tricks like, for example, if you have some idea of the more or less the type of value and some range around that, you want to, then you can invoke this argument and say, well, actually the least if I make that into a PDF, the least informative way to do that is to choose a Gaussian. That would be one way to do it. If you have bounds and you can say, actually within those bounds, any model in those bounds to me has exactly equal, any parameter within those bounds has exactly equal prior probability, then you should take a uniform within those bounds. Okay. Now, if you really know nothing, if you want to go to that extreme, which is almost never really the case, but if you really know, if you want to go to the extreme that you don't know anything about a parameter, then we can talk about, so this is an example of an informative prior. You can do bounded uniform. So as another informative prior, but then there are also uninformative priors. And we'll talk about those in a minute. Okay, but let's keep going with this example. All right, so now in building this joint PDF of my parameter, which is the true height of this table, and the data that I will take by measuring it, I have my prior, and now I need my likelihood. I need the forward model. I need to, given a true height, what value am I going to measure? So I can simulate that. If I want to draw from that distribution, well, in fact, you could take a table, or you could take some object that you know exactly the height of, and you can make me measure it 5 million times, and then you actually know what the PDF is of my, then you know, given that true height, you know how my measurements will be distributed. You could use that information. You can do that with many different tables of known height, make me measure it 5 million times each, and then you actually have a lot of information that you can use to interpret how I measure this table, okay? Because you then have the joint PDF, you use the measured information, so then you actually have the actual measurement device, which is me, and you're modeling that through empirical distribution because you make me measure lots of different tables many times. Okay, that's one way of doing it. Another way of doing it is to say, okay, I have a computer simulation of me. Now, what do I put into this computer simulation? Well, you could build like a full-scale molecular dynamics model of me, okay, with my eyes and my brain and everything, or my muscles and so forth, and measure. It's a very complicated problem, right? Because I'm a human being and I'm taking an object and I'm measuring the height of this table. It's very, very complicated, right? So that's one way of doing it. Or you could say, well, all of these sources of uncertainty of me, fact that I can't see well, and I'm kind of old, so I'm shaking, and so all that stuff together makes some uncertainty. But in fact, I'm just going to put that uncertainty into a parameter, and I'm going to say Ben will measure the true height of this table plus or minus some epsilon, and I'm going to just resum all of those degrees of freedom of like my molecular dynamics simulation into just one number, which is an error, which you also say due to the central limit theorem, because all of those sources of uncertainty, my brain, everything else, add together, and there's a result, very deep result, which is that if you add a lot of random numbers together that have, they actually tend to Gaussianize, like the total PDF, after adding all of those together, very quickly actually tends to Gaussianize. So you're then going to say, okay, my statistical model for Ben is just that he measures the height of this table, which is a Gaussian random number, with some variance, and that variance tells me the sum of all of those sources of uncertainty. Okay? So I know this is kind of ridiculous, but it exactly maps onto your kinds of problems that when you want to do parameter analysis, you always have a choice how deep to go with your modeling. You can go all the way, or you can truncate at some level and say, no, everything below this level, all the microscopic degrees of uncertainty and so forth, I'm just going to summarize into an effective statistical model. Maybe you make it Gaussian with some mean and covariance, okay? By invoking the central limit theorem, because you say, actually, a lot of different sources of uncertainty come together, they add together, and therefore by the central limit theorem, I'm going to model that approximately as a Gaussian. Okay, so it's a choice of how deep you go with your modeling. Okay, so now then I build up my joint PDF of the height. I take my prior, I write it down. I take my likelihood, I write it down. And then I have this joint PDF. And in that case, if it's just Gaussian, if I take a Gaussian prior, a Gaussian likelihood, the product of two Gaussians is still Gaussian. And because I have a linear model, okay, I said that my measurement is just the true height plus, not nonlinear function of, but just true height plus some error. I can then just add those two together. I still get a Gaussian, and it turns out my posterior that I can just read off once I've multiplied those two together, my posterior will be a Gaussian posterior, which for the parameter, which will be centered at some value with some spread around it. And the spread depends, of course, on the variance of my error and on the width of the prior distribution. Okay. So, clear? Okay. So this is sort of trivial example, but you can dig down and see that it actually has a lot of the complexities. So how do I choose uninformative priors? Let me do an example where it's very easy to see. Let's say, after this talk, I will be in urgent need of a coffee, and I want to know which way the direction of the next coffee is. Okay, the nearest coffee. All right. So let's say what is my prior? Okay, I have some information that I can get. I can ask Rishi or something, and that will update that prior, and then I get my posterior, then I make a decision based on that posterior, which is that I'm going to move in this direction. Okay, but let's say before I start, you guys are saying, wait, we're scientists. You should assume an uninformative prior on the direction to the nearest coffee. So how do I do that? How do I encode mathematically the notion of not knowing at all in what direction the nearest coffee is? Okay, that's my parameter. So at an angle, okay? So one way of thinking about this problem, and this goes back to Jeffries, so he developed a mathematical way of encoding absolute absence of information. And he said, okay, so let's encode absence of information as a symmetry. So there are symmetry transformations that I can do on my state of mind that will leave the state of my mind completely invariant under that symmetry transformation. If I have such symmetry, if I find a state of mind that respects the symmetry transformation, then I am completely uncertain about the group parameter of that symmetry transformation. Okay, that's the mathematical way of talking about complete ignorance. So for the case of trying to find where the next coffee is, the nearest coffee is, it's a direction. So what is the symmetry transformation that completely leaves my state of knowledge invariant if I really have no idea? Well, it's rotations, okay? So it's it's U1, okay, my group of rotations. So if I really don't know what the direction is, I can do any rotations and I still don't know which, it leaves that probability density invariant it doesn't matter which way I rotate, okay? So it's invariant under the action of a U1 group, okay, group of rotations in 2 dimensions. And so then I can ask, okay, so then I can solve the problem. I want to find a PDF, P, such that P of phi, phi, okay, that the probability of the direction being in any particular direction, which is probability density times the size of the the range, is invariant under that group transformation. Okay, so U1 is you can just add by adding a vector, adding an offset C for all members of the group C. Okay, for all rotations. I mean, I could have written rotation of unit vector, but you know that just shifts the angle by some amount. So if I look at this, well, d phi plus c, d of c is just a constant transformation at every one of them, so that goes, so I get just p of phi is equal to p of phi plus c, okay, and phi is in this range. Okay, so the unique answer to this, I mean, you can be formal about it. You can say this is a functional equation for a probability distribution, has to be larger than 0, integrates to 1. So the thing that solves, the function that solves this functional equation is just p of phi is equal to constant. And actually it's 1 over 2 pi, right? So that is the derivation of the so-called Jeffreys prior. The name is Jeffreys with an S, so it's Jeffreys apostrophe prior, not Jeffrey apostrophe S prior. Jeffreys prior for the direction in that particular problem. So this works very well if the group manifold of this transformation that leaves your state of mind invariant is bounded. Now, if you want to ask about what is the probability, what is complete ignorance about location, well, if you're taking the real line as all possible locations, that group manifold of translations on the real line is unbounded. And unfortunately, so what you find again is that it's constant. It's just like taking the circle, leaving some mathematical niceties under the table, and taking the radius of the circle to infinity. Well, then if you have the radius in here, this becomes 0, basically. It becomes infinitesimal. Basically, you have an infinitesimal amount of probability of being anywhere along the real line. And so you see that it is completely ridiculous to talk about complete ignorance when it comes to an unbounded set of possibilities. There never is such a thing, okay? Just an exaggeration. Now, it turns out that in many cases, even in cases where the location is in, where we're talking about location, and you're saying, really you always know something. It's somewhere on Earth, or it's somewhere in the observable universe, or something like that. It's never completely infinite, okay? But sometimes it doesn't really matter. If the prior is so flat in the region of interest, then it's just a convenient approximation to say the prior is constant, even if it's, so you don't take into account the fact that in fact, it does get bounded and cut off at some point in the, Okay, so for location parameter, therefore, so the group then becomes the group of translations, so Jeffreys prior P of, let's say, x is proportional to constant, but it's kind of, obviously the probability of it being in any particular range is actually infinitesimal. Interestingly, you can do, it's the same argument leads to this. Exactly analogous argument if for a scale parameter. So something about, for example, how wide is something, how big is something. And a scale parameter, it turns out, with the same argument, you get a different functional equation here, where P of phi is equal to P of A times C divided by, times A. And you find that the answer is that P for a scale parameter, let's say call it A, which is larger than 0. So in other words, you don't know how large something is, how wide something is. The Jeffreys prior becomes P of A is proportional to 1 over A. Again, this is not normalizable. When you integrate this from 0 to infinity, it becomes infinite, just like integrating a constant from minus infinity to plus infinity is infinite. But these are approximations if you really want to go to the extreme of saying, I have zero idea. Now, I really want to emphasize that you're never actually in this situation. These are just approximations if you're too lazy to really think about what your true prior is. And in many cases, it doesn't really matter. If you have informative data that constrains you in any kind of real, in any real way, these asymptotic arguments about what happens at infinity and so forth don't really matter. Yes? To bound the prior, well, yeah, so if for example, there's some physical reason, there's some physical bound, you can implement that and certainly use that to cut off the parameter range. And then you add this bound to your model. That's part of your model. So prior choice actually is part of your model. Intuition, I'm not sure if you call it intuition, but it's your physical model, right? So maybe then this is a good point to ask about model comparison. So how do I compare different models? There were different questions about that. Model comparison. So how do you decide? Somebody now does their has some model. Okay, you have two. We're scientists. We want to compare different models. It's kind of really at the core of what we do. How do we decide which models are worth it and which models we should toss aside? Okay, to make progress. And so let's ask Mr. Bayes what we should be doing, okay? Let's rewrite Bayes' theorem. We had P of theta given D, but I'm now going to put in the fact that I could write this for several models. So I'm going to condition everything on the model that I work with. Okay, just add behind the conditioning bar, just add explicitly that my prior choice depends on the model, my likelihood can depend on the model. So this, the physical model that we use to predict the data goes here. This is basically all possible data sets that I can predict for any possible parameter within this model choice. And this is the posterior that I get for that model, model MI, okay? All right, so now that we've talked about conditional probability and so forth, how would I, if I want to ask what do I know about the model? How probable is the model given a data set? Well, I basically already said it. How do I write this down? Probability of the model given the data set, right? So it's the conditional probability of the model given the data set. P of so we want to know, as scientists, we want to know P of MI given the data. All right, but this is not here. So we need to calculate this, but we have all the rules now from last lecture that allow us to calculate this. We have something that kind of looks like this, but isn't this, right? So let's see if we can make that connection. Well, so we can just write using, we can say, oh, this is the, if I multiply this by P of D here, I get the joint probability of model and data. So I can sort of write a Bayes identity, Bayes theorem for this, okay, which is just that this is P of D given Mi times P of Mi divided by P of D. All right, not bad. I can write this for every single model that I have in my model space, okay? In order to be able to write this, of course, I have to have several alternative models. If I only have one model, then there's no sense in which I can compare two models. If I'm assuming that that model is true, then I'm assigning probably 1 to that model, okay? So then I can't ask that question, I can't really ask a further question. But then, if I have two alternative models, then I can ask about, what is the two model probabilities have to add to 1, because if I'm saying I have two models, then I'm saying in my entire universe of possible models, only those two models exist, and therefore their probabilities have to sum to 1, given the data, right? This is the conditional probability, has to sum to 1 if I integrate or sum over this first index, first number, over this models. Okay, so in other words, if I have two models, I can just do this problem by taking the relative probability of the two models, because they have to sum to 1, and then I have the two probabilities. So that means I can get out of the question of what this is, because I can just write the relative probability of model I and model J in my model space of, we have models Mi, where I goes from, I goes from 1 to n model. Okay, so this is my, it's supposed to be, okay, so this is my set of models that I have. And I can work out the relative probabilities of all the different models by computing this ratio. And then in the end, when I have all the relative probabilities, I can just say, oh, they have to sum to 1, because that is my entire, they're mutually exclusive and collectively exhaustive. That means the probabilities have to sum to 1. And so if I get this, I get P of D given Mi, oops, divided by P of D given Mj, times P of Mi divided by P of Mj. Okay. So, great. So I can, if I have this, I can, for each model, I can calculate these ratios. This here is just the ratio, this is without having seen the data. In other words, this could be based on previous data, could be based on things like physical plausibility. Like if you really don't like a model, you can, if you think that there's some prior probability based on the structure of the model or something like this, this is the place to put it. But typically it will be based on prior data. If you want to be uninformative about this prior, you go back to this argument. Now your group space is the group of permutations, okay? Because if you don't know which model to prefer, then exchanging any two models leaves your state of knowledge invariant. And so that's a fancy way of saying that all of those should be the same. And this goes away. If you're saying, I want to claim prior ignorance about which model is more likely, more probable, you set this fraction here equal to 1. Right? Because you can. And so this quantity here emerges as the key thing that actually says how the data has an impact on what you believe about the model, how good a model is, how probable a model is given the data. And so this is called because these are called evidences. Remember? Evidence. This is called the evidence ratio. And this is why it's called the evidence, because it has the rule, because it basically tells you about the evidence for the model that you're using to construct the Bayes theorem. Evidence ratio. Or sometimes it's called, because it's such a key thing, it's called the Bayes factor. Not sure, anyway, a little strange convention to call it that, but it's sometimes called that. Okay, and how do I calculate it? Well, actually, to calculate it, it's very simple. We exploit the fact that we now understand conditional probability, and all we have to do is integrate remember this thing here is a PDF for theta only, not for D, not for M, because these are behind the conditioning bar. So I can integrate, this thing does not depend on theta, so I can get rid of this by integrating over theta, and it will make that to 1, right? So just exploiting that, I can calculate the evidence, P of D given Mi, as just the integral of P of D given theta comma Mi times P of theta given Mi d theta. This is how you calculate the evidence. And here you can directly see it's the in our picture that we keep drawing. I guess I have space for it here. Theta d. The evidence is that PDF here. So basically, from the joint, you have your joint PDF that you can use to do parameter inference. But the marginal of this, when you integrate over all parameters, is this P of D. So it's what the model predicts for the data. Okay? Regardless of the details of what parameters you choose, but the whole model predicts this PDF for the data. So in that sense, so now we can talk about why this is reasonable. So we asked Mr. Bayes. Mr. Bayes told us this is what you should use to calculate relative probabilities of models. And by using my terminology that I said I prefer, which is that this is the marginal predictive density, which is what I recalled here, we actually understand what Bayesian model comparison is all about. Because what we learn here is that the one thing that matters for evaluating the relative probability of models is how predictive and accurate the model is. Okay? It's basically those two things. Let me give you an example. Let's say I have, I want to invest my money in the stock market, and I talk to a investment advisor. The investment advisor, I have two investment advisors that I talk to, and I don't know which one to believe. Okay? Now, each one of those they both have their models. Okay? So I'm basically evaluating the two models of those two investment advisors. So it is instructive to realize that, in fact, you don't need to know anything about their models to find out, according to this, which one of those two people I should believe. I just need to know what they predict. Okay? This is the predictive density for the data. So let's say, if I want to ask, so let's say one of them predicts that, so here's the predictive density for model 1. Okay, for the data. The data is, let's say, some stock index tomorrow at noon. Okay, so, and the predictive density for model 1 is, well, it's somewhere between, 100 and 10,000. 1,000 and 10,000. Okay, so very, very broad. And the other prediction is like this. The other financial advisor tells you, I've run my models, I've done my inference, I've figured out all my economic models, and there are surely 300 parameters in the model, and this person has whatever number of parameters, but you don't need to know this. All you need to know is the outcome, the probability distribution. They tell you the predictive probability for the data under their model is that, let's say it's Gaussian distributed at, I don't know, 5,000 plus or minus 0.1. Okay, so extremely narrow. Remember, both of those are PDFs, so they're both normalized. So this, I couldn't draw this normalized on the board. Too high. And this is very wide, between 1,000 and 10,000. Okay? So of course, so who of those two are you going to believe? Let me have a show of hands. Who believes this? Who believes this? Okay, in fact, you don't have any reason to believe one or the other because you don't have the data yet. Okay, so sorry about that. So, yes, so actually in some sense, some people maybe expressed some kind of prior, they liked the model better because, this was maybe more conservative and this seems more predictive, right? So let's call this the conservative model, very broad, basically never wrong. This is the predictive model, which can be very easily wrong, okay? But gives you a high probability, very, very, very predictive. Okay, so let's take two different scenarios. Scenario one, where tomorrow comes and the realized value of the data, you measure the stock index at noon, at the following day. And let's say the answer is 5,000.03. Okay? Let's say that's, I don't know if they measure stock indices to up like that, but okay, you get the idea. All right, so now, who of you is going to believe this model? Who's going to believe this model? Okay, people are not sure. Well, Bayes tells us, okay, let's say a priori we said we don't know, so we make this 1, okay, prior ignorance. So Bayes says, okay, we evaluate these two PDFs at this value. So this here is going to give you some enormous value because this is concentrating all of one unit probability inside a tiny range around this 5,000, and this hits smack bang in the middle. So this is going to give some enormous value. This here is a very wide probability distribution. So it has a tiny value because that range, at that point, right, it's spread 1 all the way between 1,000 and 10,000, so it's going to be tiny. So Bayes says you should, aren't you surprised? Somebody tells you what the stock market is going to be tomorrow down to like 1 digit after the decimal point, and then it turns out it is exactly that. When, day-to-day variations could be like plus or minus 100 or something like this, I agree with Bayes. I think after that one day, either they got extremely lucky or they know what they're talking about, okay? So in this case, P of M 2 given D divided by, the realized value is much, much larger than 1. So assuming prior ignorance, okay, saying that this is 1, okay? Or anywhere close to 1, doesn't really matter because this is, this is a factor of 10,000 or more. So a different scenario, let's say the true value is scenario 2. Let's say D star ends up being 8,000. Okay? What the heck? So which one are you going to believe? You believe this? Who's going to believe this? Show of hands. Who's going to believe this person? Nobody. Correct, because once you go, 8,000 is 30,000 sigma away from this prediction, right? So this is going to be tiny, whereas this is kind of linearly spread over this large range, so it's also small, but much larger than this. Okay, so in this case, P of M1 given MD, so 1 wins. Okay, those are two it's a very decisive difference here. So you can see what's going on. Basically, Bayes factor rewards being right, okay, and predictive. So the person who said, so this is where your notion comes from that, you know, a good theoretical model should be easy to rule out, should be very predictive, right? I mean, a model that says all possible outcomes are equally probable. In fact, I've said this, I know this is being recorded, but that's okay. But let's say, for example, a multiverse model, okay? Let's say if it were true that multiverse models give you all possible universes with equal probability, okay? If that were true, then you wouldn't even have to go and do any observations, because according to this, multiverse model would be a priori ruled out, would have evidence 0. I mean, compared to any other model that says there are some universes that are preferred by my model than some other universes. So that other model, however wrong, would still be much, much more likely than a model that gives you equal probability over an infinite space of possibilities. Right? So if it is true that a multiverse model gives you all possible outcomes with equal probability, and there's an infinite space of outcomes, then I don't even have to do an experiment. I can already tell you, without doing anything, that the multiverse is ruled out. Yeah, I have to stop now. Yeah. Got it. All right, so that's, but if you have a by the same token, if the predictive model hits on the truth, you know, does predict well and agrees with the data, then you have a very strong reason to prefer the predictive model rather than the super conservative model that said everything's possible. You know, then you get rid of this. So so you want to be predictive. Good models are predictive. Okay, we're going to finish the discussion of that tomorrow morning. Thank you.